Today, we'll look at is solving a linear system using matrices. We looked at matrix concepts last time on Friday, and now we'll use those to actually solve a linear system. We did solve linear systems with the Laplace transform, so that's one way you can do it. But in my opinion, I think it's a little bit easier to use the matrix method personally. So let's go ahead and look at it. First, maybe some announcements. As I mentioned before, what we'll have this week, essentially after today, is review leading up for the final exam or exam 4. There won't be an explicit day for first order review, but my hope is that after doing that numerous times, that's kind of pretty well ingrained for us all. But you're still welcome to watch the first order review video, or if you've got questions about it, you're welcome to ask that today. / if you want to talk about it on Wednesday, or just email me or what have you, you're still welcome to talk about it, of course. But on Tuesday, in theory, you would want to review higher order, maybe the video. We'll have a online homework that's based on higher order concepts. The same thing. Wednesday, it's Laplace. And then Thursday, series matrix methods. All these, actually, this is a copy paste I did from a previous thing. These are actually all available now. So you can start doing the review anytime it's convenient for you. Their official due dates would be, on Tuesday for this one, Wednesday for this one, and Thursday for this one, but you can work on them whenever you would like at this point. And also, as I put as an announcement in Canvas, I've updated the final grades to include attendance and participation, and I just kind of gave anyone who has been coming to any degree, attendance and participation, just kind of to finish it out. I also replaced the lowest exam score with the highest, as was promised after the first exam. And then as I mentioned, but maybe it wasn't super clear, there's about 25 percentage points left. The final is 20% of the grade. And then with the last lab, the last written homework, and then some of the last online homeworks, there's about another 5% roughly. So whatever your grade is now, you can increase it by up to 25%. So if you have, let's say, a 60% now, that means you can get up to 85%. And then what I'm planning to do is add another 5% on top of that, depending on how it all shakes out. The reason for this extra 5% is I feel like replacing the lowest exam score by the highest was a way to kind of account for everyone adjusting to the exams, which I think is good. And now looking at everyone's score, it seems very reasonable for exam scores. Some people did fantastic and, got a 40 on one problem or a 38 or something, and then, really improved what wasn't maybe the best score for the first exam, or maybe even had a dip later and was able to use a strong first exam. Anyways, it evened out pretty well, in my opinion, for exams. But the written homework and the labs started out also with some adjustment. So this is the point of that 5% is to largely account for people adjusting to the written homework and the labs. And that's what I've got for announcements. So let me flip back a second and just give us an idea of what we want to do. We'll, of course, open up for any questions that you have, and or at least some, we'll talk about those. And then what we'll do is review some things that we talked about on Friday. Or I can't remember how much we talked about them, but we at least mentioned to some degree like how to find eigenvalues. And then we'll maybe do an example or two of those, look at converting the system to a matrix, all these setup things, and then we'll look at how you actually find the solutions once you convert a system to a matrix, find the eigenvalues, eigenvectors, and then you sort of assemble it all together. The assembly at the end is not very hard. This is kind of where all the work is. All right, with that, let's open up to questions you guys have. Okay, one question was for online homework 39, so that would be the review for the series and matrix methods. The question should be, will we learn how to do 3 and 4 today? Good question, let me look. Let's see, for online homework 39 or day 39. let's see, 3 and 4, or at least 3 we would know how to do from day 39 because that's writing the using a series solution. If you need help with that, feel free to let me know. And then for 4, certainly we will learn how to do that today. We find eigenvalues, eigenvectors of the matrix, and then assemble it to get the solution. So yes, yeah. If you need help with anything, you feel free to stay after today. If you want to get it done quick, or if you want to email me and we can talk it over. Probably meeting is easier if you're having any difficulty. All right. It doesn't seem like there's really many other questions. So why don't we actually just jump into the material right away? We can see how that goes. So the first thing is, and let me actually copy this so we have a good, nice heading. I'll do some copy paste real quick. Forgive me as I fly through this. Only take a second. Let's cut this and cut this. All right, the first part is really not very hard at all. But if you have a linear system, and by that I mean you have something to the effect of, let's say, dx dt is equal to ax plus by, and then you have a dy dt is equal to cx plus dy. It may even be obvious to you at this point one way to convert this, but after you've seen it once or twice, it becomes sort of, you can't unsee it, as it were. You notice that these entries here and how I set this up, hopefully, almost makes it look like a matrix just already. And what we're going to do is we're going to essentially just extract this ABCD and put it into a matrix. So we set it up and it looks like so. And that's really it. Now, if you had, let's say, some of these being 0, that's no problem. For instance, if you had a system of this form, then of course our matrix would just be like this. So these entries are non-zero. And then since we don't have an x in the first equation, we would just consider that to be 0 times x. And that's really all there is to it. Nothing fancy. After that, it gets a little bit more difficult. So the next thing we want to do is finding eigenvalues. So assuming that you have a matrix, so you've converted your system into a matrix, and now you want to look at the eigenvalues of that matrix. And let me just check this really quick, because if you, the eigenvalues can be real numbers, they can be complex numbers, so they can be very unpleasant real numbers. I just want to make sure we have one that will give us nice eigenvalues, or relatively nice. So let me check this real quick. I had an example and now I'm just looking for it. Okay, here's one. It's won't be as nice as I wanted, but I just want to get an example out here for you so you're not waiting too long. Let's say we have the matrix 3, 4, and -4, 8. This is, let's say, our matrix A. What we know about eigenvalues and eigenvectors is that they satisfy this equation. So if you have, and I don't know why I want to draw that a little straighter. If you have a matrix A, you multiply it by V, a vector V. So A would be an n by n matrix. V would be an n by 1 matrix. And if what you get in return is lambda, where this is a real number, lambda times V, that's what you get, then that's going to tell you that lambda is an eigenvalue and V is an eigenvector. Maybe I'll move that and put over here that lambda is a real number. And then this tells us that lambda is the eigenvalue and V is the eigenvector. Since that's just by definition what it means to be an eigenvalue and eigenvector, we're now going to rewrite that equation. And you can think of it roughly like this. You can think of it, let's suppose instead of v, we just had it like the variable x is equal to lambda x. Since you're maybe not so familiar working with matrices, this might not be comfortable up here rewriting, but it's no different than if, let's say, a was just some real number and so was lambda. You know, you would write this and then you'd factor out x and so on. This is just the idea here. We're going to do the same thing with the matrix version with one caveat. When we write it like this, AV minus lambda V, that's basically the same as before, but now we have 0 as a vector because both of these are n by 1 matrices. This is n by 1. This is, let me rewrite that a little nicer. This is n by 1. This is n by 1. And that means that this thing has to be n by 1. So if we just put regular 0 as not a vector, that wouldn't make sense in terms of dimensions. And then the other thing is that when you quote unquote factor out, since A is an n by n matrix, but lambda is not, since it's just a 1 by 1 matrix, if you will, it's just a number. In order to get the dimensions right, we need to multiply by I. Now, this thing is an n by n matrix. And that gets multiplied by V. So here's the quote unquote factoring out. And then at this point, what one can use is what's called the inverse matrix theorem, which is a huge theorem in linear algebra. So if you ever study linear algebra in the future, you will come to know this intimately. And it's basically a theorem that says something ridiculous, like 20 different statements are all the same. What that says is the inverse matrix theorem says this implies, so the green is the inverse matrix theorem. And I should say one more thing. This together with the fact that we take V to not be equal to 0. I should really say both of these together is what the inverse matrix theorem will give us. That these two things together are equivalent to saying the determinant of this A minus lambda I is equal to 0. And I'm going to move all this over a little bit. So long story short, if you've got a matrix, let's say like this, we use the definition of what it means to be an eigenvalue and eigenvector. We do a little bit of matrix algebra, which is to subtract this matrix on both sides, giving us this, leaving us with the 0 matrix on the right side. Then we quote unquote factor out the V. That's a little more matrix algebra, where since we're working with matrices, we got to make sure we keep dimensions when we add, subtract, and multiply. Everything has to have the right dimension. Since lambda by itself is just 1 by 1 and not n by n, we multiplied by the identity matrix. Just real quick check so I get a sense of where you guys are at. Will you tell me if you know what the identity matrix is in n by n or not sure? Either way, doesn't matter. I just want to know, should I say what it is or do you guys get it? Okay, I see at least a few not sure. That's okay. It's, I think, something that won't be hard to remember once you see it, but it certainly can seem mysterious at first. So the identity matrix is, well, it depends on what dimension you're looking at. If it's an n by n, if let's say you have I2, for instance, that's going to be 1 on the diagonals, 0 elsewhere. If you have, let's say, I3, you're going to have, again, 1 on the diagonals, and 0 elsewhere. So it's an n by n matrix where you have ones on the diagonal and zeros everywhere else. The reason it's called the identity matrix is that if you multiply it by any other appropriate matrix, you get the original back. So for instance, if you took A times the n by n identity matrix, you would get A back. So it's just like, it's like the number one, but for matrices. It maintains the identity of the matrix when you multiply. Okay, so the idea is you take lambda times the identity to get an n by n, and now you're going to take the determinant of this thing. This whole thing, once you combined, is going to be another n by n, and then we looked last time that you can take the determinant of any square matrix. And what the inverse matrix theorem says, so I'm going to maybe shrink this a little bit so it doesn't distract us too much, but if you want me to enlarge it, just let me know. So this is like a little note down here. So what the inverse matrix theorem says is that we essentially jump to this here. Okay, so that's fine. This is some math, some linear algebra, matrix algebra type stuff. That's cool. I like it. It's a thing that matters to some engineers and scientists more than others. Some people use it all the time, some people not so much, but okay, it's just some math. Who cares for us? Why we care is if we want to find eigenvalues, what this means, this couple steps, and the fact that there's the inverse matrix theorem, it means that we want to take the determinant of this expression. And if we take the determinant of that, set it equal to 0, in theory, what we could do is find lambda. Okay, for instance, with our particular matrix, we said we want to compute the determinant of A minus lambda I. One notation for the determinant is dt. Another notation is just absolute value bars. Now let's think about, actually, maybe I'll do it this way. I'll save the absolute value bars for a second. Instead, we'll just look at what this is. A is 3, negative 4, 4, 8. Then we're taking minus lambda, which is something we're trying to find, minus lambda times the identity matrix, which is 1, 0, 0, 1. Multiplying a scalar, or just a number, times a matrix, you just multiply each entry of the matrix by that number. So what you get, and I'm going through this sort of more than I would normally, just for the sake of making it really clear. And if you've got questions, of course, feel free to let me know. I'll be the only one who sees it if you private chat me. But we'll have 3 minus lambda. Or actually, if you really want, let's make it even more explicit what's going on. So we have minus lambda 0, 0 lambda. That's just the scalar multiplication. And then that turns into 3 minus lambda minus 4, 4, 8 minus lambda. Okay, so we're computing the determinant of this expression. We end up with this. Now, to take the determinant of this, what it will end up being, and let me maybe move this up a little bit, is it will end up being 3 minus lambda times 8 minus lambda minus a negative 16, so plus 16. And that will be, let's see, 24 plus lambda squared minus 8 minus 11 minus 3, so minus 11 lambda plus 16. And it looks like that will be, if we simplify it, be lambda squared minus 11 lambda plus 40. All right, so we started with a matrix. Here, we said we wanted to find eigenvalues, which is lambda, and we end up with this polynomial, second degree. Well, it's exactly the same as when we looked at spring mass systems and we got the characteristic polynomial. Here we have a polynomial in degree 2, variable lambda, but same idea. We can get 3 different types of sets of roots. We can get 2 distinct real, repeated real, or we can get complex. So it doesn't work any different than the spring mass case. And actually, maybe I'll put this, let me put this here. And to note, this can go in one of 3 directions. It can be distinct real, it could be repeated real, and it could be complex conjugate pair. So you have the different possibilities. In this case, if we actually compute it out, what we'll find is that lambda will be, let's see, 11 halves plus or minus 1/2 times square root of, let's see, 11 squared, which is 121, minus 4 times 1 times c, which is 440. 4 times 40. And if we compute that, what is that going to be? 39i. So we get 11 halves plus or minus, oh, sorry, root 39. Root 39 halves times I. So we get a complex conjugate pair. But in the end, it all came from this polynomial here. So setting up this polynomial will allow you to find what these are. Now, there's another method that will work in any 2x2 case, but it's really when it's going to be useful is when the eigenvalues happen to be nice, like they're both integers or simple fractions. In this case, I don't think it would be so nice, but you can use the trace and determinant of the matrix just itself without computing the determinant here to find them. But let's wait a second to do that. Instead, let us maybe do the following. Let's look at finding eigenvectors. And actually, let's use this example. Where did I have it? Just had it up. Okay, here it is. So let's say we did a 3 equation system. And what we got is this matrix. A is equal to 2, 1, 1, 1, 2, 0, and 0, 0, 2. Now, just as a reference, we won't go through this, but what you would get if you took the determinant of A minus lambda I, where I is a 3x3 matrix, in this case, because A is a 3x3 matrix. If you took this equation here, what you would get is a 3rd degree polynomial. And from that, you would get up to multiplicity 3 eigenvalues lambda. And finding them is as simple or as hard as just solving or finding the roots of a 3rd degree polynomial, which you could have 3 distinct complex or 3 distinct real roots. You could have a complex pair and a real root, and so on and so forth. You could have some combination of repeated real roots, but you're going to have 3 up to multiplicity, and some of them could be complex. Let's say we know that one of them we found, and what we found is that lambda is equal to, let's say, 3. Now what we want to do is find eigenvectors. You should always find the eigenvalue, for this case. I always find the eigenvalue first. And then you're going to find from each eigenvalue, you're going to find an eigenvector. So in this case, we're going to use that same equation that we looked at before. We're going to say that A times V should be equal to lambda times V. Now let's say that V is going to be equal to X, Y, Z. And of course, our lambda is going to be equal to 3. Let me actually move this onto the next page. All right. So what we are saying is that A times V is equal to lambda times V. And if we take and write that, let's say here, what we get is that lambda is 3. We get that V is this XYZ. And our matrix A is going to be given as the 2, 1, 1, etc. So we're just substituting everything in. And now if we multiply all that out, which I'll move over a little bit, actually, let me put a dividing bar. If we multiply all this out, what we end up with is, let's see, 2x plus y plus z, and then 3x. Then we have x plus y, period. Then we have 3y. Then we've got, let's say, 2z and 3z. So what that gives us is this matrix, which is a vector. It's just a 3 by 1 matrix, 3 rows, 1 column. And then over here, of course, since it's equal, we also have a 3 by 1 matrix, 3 rows, 1 column. Now, what this gives us is another system of equations just arranged as a matrix. Let's say in the bottom case, we have 2z is equal to 3z. And of course, that tells us that z is equal to 0. Then in the second case, or second row, if you will, what we have is x plus y is equal to 3y. And rewriting that tells us that we have, let's see, 1 half x is equal to y. I claim at this point this is actually all we need to be able to find what the eigenvector is, or an eigenvector is corresponding to the eigenvalue 3. Now, what we've done is we've found out some information about the entries of V. We said that V, of course, is just as I've written up here, which I can even just copy. It's going to be X, Y, Z. Okay, well, what do we know about these values now? We know that Y is equal to 1 half X, and we know that Z is equal to 0. So we can substitute those things. I'm going to zoom for a second just to erase. We know that, or we can just leave X as itself. Then we'll use the fact that 1 half X is equal to Y. We'll make that substitution. So we say Y is 1 half X. And then we said that Z is equal to 0, or that's what we were told by this formula. If we substitute that in, Z is equal to 0, we get this here. Now, this may not seem helpful, but it's actually everything we need. Should the second row be X plus 2Y? Yes, it should, which will change this a little bit. Thank you. Good catch. So we got 2Y. This is 2Y, which means this is just X is equal to Y, which means, again, I'm going to zoom in, zoom out. That means Y is equal to X. Okay, good. Thank you for the catch. Now, I claim this is what we want. We have everything written in terms of a single variable, which is good because you can think of that variable as being a constant, which once you substitute in a value for it, it becomes, so you can factor this out, X, and we get 1, 1, 0. And our eigenvector is this vector 1, 1, 0. So this thing is the eigenvector. Now you can actually have other ones. This is just an eigenvector. You could have 2, 2, 0. You could have -3, -3, 0. You could have any multiple of this. So if you just take this number and you multiply it by some other real number besides 0, you get another eigenvector also corresponding to lambda is equal to 3. But usually you just want to pick whatever quote unquote would be the simplest one, whatever that means to you. Try to have as many ones as you can. Um, if we had 2, 2, we could simplify that down to 1, 1, which is nicer. If you had like 1, 1/2, you may want to multiply and get 2, 1, and so on. Pick whichever one you find most convenient. It doesn't matter for the sake of the correctness of the solution. So we go through this process, we find equations that will give us relationships between the different variables so that we can write it in terms of one variable, factor that variable out, and what we're left with is an eigenvector. And so a question is asked, how many eigenvectors are possible from the number of eigenvalues? It's essentially one eigenvector per eigenvalue. So if you have 3 eigenvectors, like this would just be one of 3 in this. And as I say that, actually, I should be a little bit more careful. If you have distinct real eigenvalues, for each one of those, you'll get a different eigenvector. So you'll get three eigenvectors. If you have, let's say, some complex numbers, you can actually just, like if you have a complex conjugate pair, you can just get one eigenvector and then use elements of the eigenvector. You could get an eigenvector with complex entries and kind of split that into 2, if you will. But in a general sense, in a non-technical sense, roughly for each eigenvalue you have, you should get an eigenvector. And that's 100% true in the case of distinct real eigenvalues. And then if they're complex, it's essentially true. You'll get one and you'll kind of split it into 2 parts. So 1 per eigenvalue is the thing to keep in mind. So if we had, let's say, further eigenvalues of, let's say, and this is not accurate because I haven't found them explicitly, but let's say if lambda was 1 and lambda was -7, we would find another eigenvector for lambda is equal to 1, and then we find another eigenvector for lambda is equal to -7. Okay. Now we talked about how to set up the system. That would have been right here. And if it's a 3 by 3 or whatever, it works the same way. So just now that we've maybe gotten a little bit more comfortable with this, just to kind of extend it. If you have a, let's say, dx1 dt down to a dxn dt is equal to, let's see, how do I want to say this? Say a11 x1 plus dot 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 plus a1n x sub n and dot 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 down to an1 x1 plus dot dot dot, like so. If this was your system, and I'll move some of this over. So you had n variables, you had n equations, then unsurprisingly, I think, your matrix would simply be the n by n matrix, a11 up to a1n, down to an1, down to ann. And then you just extend the notion of finding eigenvalues and eigenvectors of this. But once you've done this, in whichever case, whether it's 2 variables, 2 equations, whether it's n variables, n equations, once you've found the eigenvalues and eigenvectors, you want to consider what form those eigenvalues come in. Are they real? Are they complex? Depending on what you have, there's different ways you will write the solution. They actually come from essentially the same form, but in the case where it's a complex conjugate pair, you can write it like so. Now, both of these cases assume that we're just going to be working with 2x2 systems. So 2 equations, 2 unknowns, or 2 variables. And what we do is we find the eigenvalues, and either it's going to be 2 distinct real eigenvalues, and we'll leave the case for repeated eigenvalues for the moment. But if we have 2 distinct real eigenvalues, then each one of them has a corresponding eigenvector, and we assemble it into this form. So this is essentially a C1 times a first solution, C2 times a second solution. And the difference is now we have vectors that we're also multiplying by. So we have more than one level, which should make sense because we come from a linear system. And if we solve, or if we have, let's say, dx dt is equal to ax plus by, dy dt is equal to cx plus dy, well, our 2 dependent variables are x and y. So we want to find solutions that involve x and y. And how you can think of v is like so. Maybe I'll put it over here. You can think of v as x over y. So these vectors v1, v2, what they do is they give you a top row, which corresponds to the x solution, and then they give you a bottom row, which corresponds to a y solution. And that's because, again, we want to solve for x and y, and this will then give us the top row x solution and the bottom row y solution. And that's one reason to maybe help you remember why you would have eigenvectors here, is you need to have the 2 rows to account for the 2 different solutions. You're solving for x and you're solving for y. In the case of the complex conjugate pair, one way we can write it, and you can do actually the same thing up here, where your eigenvectors will have complex entries, and then your eigenvalues will be a complex conjugate pair. But using Euler's formula and rewriting blah, 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 what you can actually find is that there are real solutions that don't have any complex parts, again, due to Euler's formula. And you can write it like this, where you just use a single complex number, you find a single eigenvector, which will have complex number entries, and then you divide up this thing. Notice that's w times e to the lambda 1 times t, as is this. You divide it up into a real part and an imaginary part. And because taking the real part gives you something that's just real, taking the imaginary part is something that's also just real, then you'll get something that's completely real. And I should maybe move this over for uniformity and say this is equal to xy. Okay, so this is how this is going to look. If you remember this formula, this is sort of the base one that I would remember for sure. And then from there, kind of think about what would change if you had a complex conjugate pair instead of just distinct real eigenvalues. That's how I remember it. It's like this, and then you sort of modify it when you get to the complex conjugate case. All right, let's look at an example. All right, let me pull up this example here now that we've gotten. And to help with color coordination, let's maybe call that, there we go. Okay, let's bring up an example here. Okay, let's do this one. Say we have the system dx dt, oops, is equal to 5x plus 2y, and then dy dt is equal to just negative y. Then we have something to the effect of x of 0 is 2 and y of 0 is 1. All right. Now we'll convert this to a matrix. The matrix we would get from this, and make sure this is a little more in line. The matrix we would get is A is equal to 5, 2, 0, -1. Now from here, what we want to do is find eigenvalues. That would be the first thing. And then from that, find eigenvectors. And then finally, Avengers assemble them all together. To find the eigenvalues, we'll set up a particular polynomial. So if we look at doing part 1, we want to take the determinant of a minus lambda I, or we're going to solve for lambda, set that equal to 0. Or actually, let me put the 0 first. And in this case, what we get, I'm going to write this. If you're not sure why this is the case, let me know. But what we should get is -1 minus lambda times 5 minus lambda minus nothing. That should be it, which tells us that the eigenvalues are going to be lambda is equal to -1, and lambda, say that's lambda 1, lambda 2, say is equal to 5. Now from there, we want to find eigenvectors. We want to do this for each one of the eigenvalues. So doing part 2, say we're looking at lambda 1 is equal to -1. What we do is we say a times v is equal to lambda times v, where, as a reminder, v is equal to, let's say, xy, like this. And if we take a times v is equal to lambda times v, that's saying that 5, 2, 0, -1 times the vector xy should be equal to -x, -y, because we're multiplying by this lambda 1 is equal to -1. And if we multiply all this out, what we get is 5x plus 2y is equal to -x. And then we get, let's see, -y is equal to -y. So we don't get any useful information from the second one. And in the case of a 2 by 2, I claim you only need one useful equation. The first one will give us plenty. So we now take this and we say, it follows from this that, let's see, 2y is equal to -6x. Said another way, y is equal to -3x. And someone asked, why is there 2y rather than 2x in the top equation? Yeah. So what we do when we do matrix multiplication is we multiply row by column. So this is the row. And then this is, let me make that a little more noticeable. This is the row. And then this is the column. So the 5 is multiplied by the x, giving us 5x. And then we take 2 multiplied by y, which gives us the 2y. So when you multiply matrices, you always go row times column. And the same thing here, it's row times column. So that gives us x times 0, or no 0. And then -1 times y gives us -y. Now we said v is equal to x, y. We then found that y is equal to -3x. If we rewrite this, and let me highlight this fact, if we use this fact, y is equal to -3x, what we can then say is that V is equal to X. Leave that alone for a second. And then Y is negative 3X. So we say negative 3. Now we have this vector all in terms of one variable. We can factor out that variable, and that leaves us with 1, negative 3. And this would be an eigenvector. There are many, but this is one that corresponds to this eigenvalue here. So we have found an eigenvector for this eigenvalue. Now that was doing it for one eigenvalue, but we want to do it for another. So let us take this, put it on the next page. And what do we know so far? We've got eigenvalues known. I'm going to divide this up a little bit. Oops. And actually, for the sake of space, I can move this over a little more to give us the space we need to be able to record what we've done so far. So we found eigenvalues. What those happen to be where lambda 1 is equal to negative 1, lambda 2 is equal to, actually, I got to check, was it 3? No, 5. Okay, 5. Then we started to find eigenvectors. We found, maybe I won't put a green check yet because we haven't actually found them both, but we did find one. We find, let's say, V1 is equal to 1, negative 3, which I'll double check. Yeah, 1, negative 3. We've got to find one more, that is V2, corresponding to lambda 2. So we're still on 2, 2 continued. We then say that, as always, A times V is equal to lambda times V. Okay, so we're going to take, and let's say lambda 2, where lambda 2 is equal to 5. And now that's saying that 5, 2, 0, negative 1 multiplied by x times y, we already said that's what V is equal to 5x times 5y. That's what lambda 2 times V is. Now, if we, let's say, multiply this out, what we get is 5x. Again, it's going to be row times column. So we take this row times this column for the first entry. And what we end up with is 5x plus 2y is equal to 5x. And then, of course, we get negative y is equal to 5y. Now, what this tells us in either case is that y is equal to 0. And this says it in both cases. So it just gives us the same information twice. Thus, what we can do is we can say that V is equal to xy is alternatively equal to x times 0, which written another way is x times the vector 1, 0. And now that 1, 0 is our other eigenvector. We can now say our V2 is equal to 1, 0. So we've now completed this. Okay, with that, let's give everyone a chance to check in. Would you private chat? Either way, just tell me if you're getting this or not, how it's going. So if you're getting it, you can just tell me that. If you're having trouble, that's fine too. Let me know. There's no wrong answer in this case. It's just where you're at. Okay. For those of you who put something in chat, I appreciate it. It looks like the consensus it seems to be making sense. That's good. Now, the very last thing is to, like I said, do Avengers Assemble here, where we actually put it all together. And what we have in this case is distinct real eigenvalues, that is -1 and 5. So what we can do, I'm going to jump back a little bit, jump back to here. In pairs, lambda 1 goes with v1, lambda 2 goes with v2. So these two go together, these two to go together, but they always go together in the same form. It's always the vector times e to the eigenvalue times t. The vector times e to eigenvalue times t. So this is how we're going to assemble. Let's see. I would like to clean this up a bit. So let's do a new page where we just see the assembly because we have everything we need to know right here. All right, the assembly goes like this. It is V, which is just an XY. So just to be clear, this is like X for the first entry. This is Y for the second entry. Let me rewrite a little nicer, which we'll just call V sometimes. This is equal to C1. And now we take V1 times e to the lambda 1 times t. Then from there, so see it's all C1, V1, lambda 1. And the next you can guess is going to be the same thing, but now we're going to have C2, V2, e to the lambda 2 times t. If we then substitute, V1 we said is 1, -3. Then we had e to the lambda 1, so that's negative t, plus C2, V2 is going to be 1, 0. And then we're going to have e to the lambda 2, which is 5 times t. And now that's fine. Like this is a perfectly fine way to write this. Another way to write it, which will, I think, maybe make it more clear what we've actually done overall here, is we'll multiply the C1 times both of these entries, and then we'll take e to the negative t times both of these entries. Then we'll add it all together. I'm going to write this. It may be really clear what's going on. It may not. And if it's not, that's okay. But what we would get is a single vector like so. C1 e to the negative t. Why did I get that? I got that because I took C1 times 1 times e to the negative t. That's in the top row. Then the same thing over here, C2 1 e to the 5t. Looks like a Super Nintendo controller. Then we're going to add those together, and that's because it's in the top row. So we get plus C2 e to the 5t. And then again, we had all that coming from the top row. So here, and then we added that up, and then we got this. So all this is top row stuff. In the same way, bottom row stuff would be like C1, -3 e to the negative t, C2 times 0. And that will give us just C1 e to the negative t. I'm sorry, -3 C1. And then we get this here. Okay, so why rewrite it like this? Well, now we can see this was the vector xy. The first entries must be equal. That is, x should be equal to this since they're both on the top row. And then y should be equal to this. So now we know what x is. We know that x is equal to c1 e to the negative t plus c2 e to the 5t. And then we know that y is equal to -3 c1 e to the negative t. And as general solution formulas, we've got exactly what we need. If we want to now know what C1, C2 are, well, it's pretty much what you would guess it would be, where we have x naught or x of 0 is equal to 2, y of 0 is equal to 1. Now you can substitute. And actually, let me move all this work. So we've done the assembly. We've done part 3. And now if we wanted to actually compute for these parameters, so let me maybe put here that we have assembled it. And now we can solve for the parameters. We let x of 0 being equal to 2. That is when t is equal to 0, x is 2. And then when t is equal to 0, we get that y is 1. Computing that, we will get 2 is c1 plus c2. And then 1 is equal to negative 3c1. And then, of course, I think you can see where it goes from there. C1 is equal to negative 1/3. And then let's see, what should C2 be? C2 should be, let's see, 7/3 minus 1/3 would give us 6/3. So that should be 7/3. Okay. Now this was going through distinct real values. I don't have time to run through, let's say, the whole process for now, a case of complex. So let's kind of skip part of the beginning because the beginning will be very similar. If you end up with complex roots or complex eigenvalues, that's okay. You can go through and you can actually do the exact same thing for finding what the eigenvectors are. Your eigenvectors will now have complex entries, which is okay. But then the question is what to do from there, what to do with the assembly. So let me just set that up. So we'll skip the first few steps just for the sake of time. We don't have the time to kind of go through it all in detail, but don't be intimidated by complex numbers. The idea is largely the same. Say you have a linear system. I won't write it because we won't have time to go through it, and I don't want to try to think of a good case offhand. So let's say linear system has, and we'll say a 2x2 linear system, has eigenvalues 2 plus or minus I. Oh, and now I realize I'm a fool. We will need, we'll actually need to know what that is to find. No, that's not true. Let's say it has eigenvalues like this, and aha, I'm not a fool. This will work. It has eigenvalues like so, and eigenvectors, or let's say eigenvector, singular, maybe 1 plus I and negative 3I. Say it's this. So if you have complex eigenvalues, you'll get complex eigenvectors, but it works all the same. Just think of complex numbers as just a little bit stranger version of real numbers, but largely all the algebraic rules hold. So it's nothing too crazy. Don't let it intimidate you. Now, once you have that and you do the assembly, it's going to be slightly different, or it can be slightly different for the complex case. So you could write V is equal to, you could have two eigenvectors and you could write like C1, V1, e to the lambda 1, t, and C2. You could do all this. What you can alternatively do is the following. So instead of writing it like this, you can take and write it in a real way where you'll actually be devoid of any imaginary parts by saying, take the real, maybe I'll call this W quick, take the real part of W times e to the 2 plus I times t. Then take C2 times the imaginary part of W e to the 2 plus I times t, like this. Okay, well, how does that work? Let's see. And actually, I see that the time's going to be up in a second. Of course, you're welcome to head out if you want. Otherwise, I'm actually going to work through the rest of this so it stays on the video. So when I post the video later, you can either watch it there or you can stay and watch and ask questions live if you want. I'll leave it up to you, but feel free to head out if you would like, since our time is essentially up. Otherwise, I'm going to keep working through this for the sake of the video. Okay. For those sticking around or still watching, let's go through this idea. So again, we supposed we had a 2 by 2 linear system. We found that it had, or we supposed that it had these eigenvalues, just as an example. And suppose one eigenvector that it came up with was this here. Now let's see how we can write it in this way, where we're going to take a real part of this and we're going to take an imaginary part of this. So let's just do this part separately, and then we'll just take the real and imaginary parts. So where we want to end up is with V looking like so. And in order to get there, what we'll do is a little bit of computation. So W e to the 2 plus IT. All right. Well, first W, there's 1 plus I and negative 3I for W. Then e to the 2 plus IT, well, we can write that, of course, as e to the 2t times e to the it. Now what we're going to do is we're going to rewrite that it using Euler's formula. First, let me copy this. But now we're going to take e to the it. Maybe I'll color this, I don't know, Euler's formula seems like a green thing. We're then going to rewrite this in the following way. It's going to be cosine of t plus I sine of t. And this is, again, for reference, this is Euler's formula. And this thing pops up quite a bit in math and, well, especially applied math and physics and engineering. So this is a good thing to really remember, try to remember if possible. All right, we've rewritten this here. So what we're going to claim is that we want to find the real part of this thing, and then we want to find the imaginary part. So there's a little bit of multiplication to do, but not really that much. We're going to notice that there's a real part here, which will get multiplied by a real part here. Then there's an imaginary part here that gets multiplied by this real part, and kind of so on. That there's going to be 4 terms that we're going to essentially get. If it helps, we could also write it this way. Maybe I'll do this. So we have 1 plus I, negative 3I, and I'll just distribute this 2t. So I don't know, maybe that will help to digest it a little more. And now what I'm going to claim is if you do the algebra, we get, 1 times this thing, and then we get I times this thing. So there'll be a real part that is e to the 2t cosine of t minus e to the 2t sine t. Where did that come from? Where did we get the minus? The minus came from taking I times I e to the 2 sine t. I squared is, of course, negative 1. That's what gives us this negative here. And then, correspondingly, I'm going to need to move this over. We have from the imaginary parts, we've got I times this, so that's then imaginary. And then we have 1 times this, which is also imaginary. So there's plus I times e to the 2t cosine t. Let's see. plus e to the 2t sine t. And move it over yet again. And in a similar way, what we end up with on the bottom is, I think we're going to have a real part that's 3 e to the 2t sine t. And then we're going to have negative 3i e to the 2t cosine t. And this will give us this here. All right, this is getting a little cramped for my taste, so I'm going to put this on another page where we have this, we've got this, and then we only need this part. Okay. So we said that w e to the 2 plus I t is equal to this thing. And of course, that we can partition into the part that has real entries, which I'll highlight here. Let's do reddish for real, or magenta, I guess. And then let's go for real red. And then we'll go here, which is going to be the imaginary. Now we can then write two different vectors. We can write one vector that just has this real part. Oh, no, that's not what I wanted. Copy, paste, and then we'll have the second part, which is imaginary. So there's I, and then times this cyan, but without the I, because we factored out the I. And you can see that individually, each vector is made up of real parts. So now we would say the real part is exactly what we've put in red. And then the imaginary part is exactly what we've put in cyan. And that's it. So I won't actually physically replace it just for the sake of keeping it coherent on one screen, but that would be the last thing to do is now take this and take this here and replace it with this, and then take this and replace it with this. And that's how you do it in the case of complex numbers. Okay, with that, that is it. For those of you still around, you're welcome to stick around and ask questions, but otherwise, you have a good day.
To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.